Hey everybody, welcome back. This is part 3 of our 6.1 notes. So we're getting ready to rock and roll and finish up here. So we're starting out with 6.1 part 3, electric fields. We just should have talked about the pith ball lab, that kind of thing, drawing the flow of electrons as we brought a rod towards there, what happened to the electrons as they traveled up, and that these should have spread and all that kind of stuff. So that's where we just came from. So now we're going to talk about the electrical field. Now, what's important about an electrical field is really the electrical field strength is all about the energy that you feel, okay, around that. And really what that is the amount of force, if you will, okay, over how many or whatever the charge is. So our electrical field is the amount of energy that you feel. Like it's almost like a force field almost. You almost feel like, how could I get in here? If you're a sci-fi person, it's like, how strong is the force field that we come in there at? Okay. And that energy that we would need is the amount of force over how many charges. And we'll work through that. So first of all, we've talked about gravitational fields before. Okay, that was G. Okay, now we're talking about electric fields. Gravitational fields deal with incredibly large things like planets and solar systems and masses, while electrical fields deal with super small point charges. Okay, instead of mass, we're using Q. Okay, these really small things. Okay. Remember with field lines, positive. If you're a positive person, you radiate outwards. If you're a negative person, you feel like everything comes in. And remember, the number of lines uh, directly relates to the strength of that field. And just to show you there's three different ways you can think about fields, okay? First of all, on a sphere, everything goes out at a right angle. This is positive, so we're all leaving, okay? Poles, okay, like a planet, have a positive and a negative pole. Okay, they're called dipoles. Di meaning two. Okay, dipoles, where one is positive down here, this would be positive, and this one is negative. Okay, and that's actually what like the Earth is, and we have a magnetic field. A uniform field is when we talk about like the surface of the Earth. Okay, the surface of the Earth we assume is linear. So we assume that it is a uniformed field, that the field only moves in one direction everywhere we look. So real quick here, you can see the different strengths and how they correlate. When you have two positives, we have some repulsion here. When we have a positive and negative, we have some attraction, or two negatives, we have some repulsion, if you will. Again, if we have a positive and a negative, we have some attraction. And again, same thing here. So, first of all, take a second. I want you to answer these. So, I want you to pause the video real quick and take a guess. Are these positive? Each of these letters, are they positive or negative? So, go ahead and take a second and then take a guess. All right, welcome back. This should be pretty easy. If it's going out, if you're going outward, you're a positive person. So, this one would be positive. These are coming in. So, this is negative. All right, this one is, yep, you're right, positive. And this one is negative. We look over here. Oh, this one is actually negative, and this one is actually positive. And then finally, all of these they're all repulsion, and they're all going outwards. So these are all positive. Hopefully that was super easy. All right, now let's see this. Let's rank their strengths now. Okay, let's rank their strengths. So you think about it like this would be the biggest. This one is greater, right? You guys all know about the alligator. The alligator eats the bigger one, okay? Whatever the greater field is to this one. So go ahead and take a guess and try to rank all these, and then we'll be right back. All right, coming back. So remember the amount of field strength goes with the number of lines. So A has more lines than B, so we're going to say that A has a bigger field strength than B. All right, obviously here D has a greater field strength than C. Okay, this guy right here. Now you got to kind of look a little bit more. So I like to think about which one's either the greatest first or whichever one's the weakest first. So the weakest would be G is less than E, which is less than F, or F is greater than E, which is greater than G, whichever way you want to think about it. And then you look right here, and I know it's a little confusing, but it's actually J, H, and then I. Again, pretty simple thing there, pretty simple thing there. But if you are lost on that, make sure you ask me a question. All right, there's this that we already did this. We did the field hockey one. It's a very similar to this one. Remember the field hockey one had the one with the goal and you had to take a charge and you had to try to send it in like a puck. Okay, this is very similar. So you've kind of already done this. So you don't need to do this right now. All right, so here we go. With electrical force, we have a new equation. It's really not that new, and I'll show you on the next slide. But the force of the field is equal to K Q1, Q2 over R squared. Well, this is obviously radius squared. These are charges. They each be a charge. You could have one charge or you could have two charges, depending on what the problem is. And then K. You have to memorize that K is 9 times 10 to the ninth. Now, again, K is a really large number because these are going to be really small numbers. Okay, these are going to be really small numbers. And since they're small numbers, we got to kind of counteract it with a constant that is large so that we can use numbers that make sense to us. Okay, and that's called Coulomb's constant. All right, the relationship between F and Q, they are direct. If F goes up, then Q goes up. The relationship between F, force, and radius is inversely. If F goes up, R goes down. If R goes up, F goes down. And again, that's just manipulating algebraic things. All right. So again, I told you this is a new equation. This is kind of what we're talking about down here, right here. Well, actually, it's very similar to what we did already when we talked about gravitation. Think about it. Gravitation was big G m1 m2 over d, or r squared. Sometimes they write it as d, but we tend to think of them as r. I'll just put r there so we all know that those are r's. Okay, but the idea is, remember, this is a really small number to counteract large masses like two planets next to each other. Okay, so this is a very large attraction, Newton gravitation, while this is Coulomb's very small, but everything's pretty much the same. It's just that the constants are different. Okay, the G is different than the K, but everything else is pretty much the same. All right, remember I told you have to know this, that an electron has this charge, a proton has equal but opposite charge. Remember, the mass of an electron is really small, but the masses of a proton and neutron are equal. These are just constants that you'll need to know and refer back to if they ask you in a problem. Coulomb is a charge of that many electrons. Okay, it takes that many electrons to make 1 Coulomb. And so you can kind of work yourself through that. All right, let's look at an example real quick. If a 5, anybody remember what this symbol is right here? The symbol right here, that's micro. That's micro. That's times 10 to the negative, who remembers times 10 to the negative 6? Yes. Nano is 9. Micro is times 10 to the negative 6. So 5, so you might as well write this as 5 times 10 to the negative 6 coulombs. Okay, 5 to the negative 6 coulombs. Point charge is placed 20 centimeters. Do you think we're going to be able to leave that in centimeters? No, didn't think so. All right, not going to be able to leave that in centimeters. We got to change it to meters. That means there's 100 centimeters for every 1 meter. So 20 divided by 100 is 0.2 meters. Okay, and then 10 microcoulombs. Now you can either write that as 10 times 10 to the negative 6, or what you're going to see, right, is we don't usually leave it like that. We move it. It's 1 times 10 to the negative, right, 7, or excuse me, to the negative 5. Okay, but we're going to leave it. I'm just going to talk about it as 10 times 10 to the negative 6. All right, calculate the force experienced by this, and we'll walk through that. What is the force on the 10 microcoulomb charge, and then what is the field strength? And remember, field strength, again, field strength is E, field strength, equals the amount of force that we're going to calculate divided by how much of the charge there is. So we're going to go over this other slide real quick. So the first one said, calculate the force experienced by the 5 microcoulomb charge. Okay, so what we do here is we use our equation and we look. So Q1 is our 5 microcoulomb. Our Q2 is our 10 to the negative 6 coulomb. That was from the other page right here. Okay, our radius is 0.2 meters. Good. Remember, this part right here, the 9 times 10 to the ninth, that's K. Okay, that's K. That's a constant. We know that. We talked about that. All right, and we plug and chug and we get this. And remember, what is this? This is a force. This is our F. Okay, this is a force. Now, question 2 says, what is the force on the 10 microcoulomb charge? We just figured out what the force was on the 5 microcoulomb charge, but now it wants to know what is the force on the 10 microcoulomb charge. So a lot of people are just going to times this by 2. That would be incorrect because we have to remember about Newton's third law that says for every action there's an equal but opposite reaction. So if there's this much force that's experienced by the 5 microcoulomb charge, it will be the same force experienced by the 10 microcoulomb charge. Okay? And that's really important because we don't want to double it. This is like when we had the bug hit the windshield and the windshield hit the bug. That's this whole problem right here. Okay. And then finally, what is the field strength? Okay. Well, think about that. We just talked about that. If the field strength, okay, is the amount of force divided by the amount acting on that charge. All right. So we take our 11.25 and we divide it by 5 times 10 to the negative 6. Now, some people are going, well, why didn't you divide it by times 10 to the negative, or 10 times 10 to the negative 6? Because it specifically asked, okay, what is the field strength from this charge? Well, since it's from this charge, we have to assume we're talking about the same thing as problem number 1. We're trying to figure out the force that charge is producing on to the 5 coulomb charge. So we have to use that force and divide it there, and we get that answer right there. And again, we'll work through this a little bit more. Uniform field strength, again, no matter where we put a positive point charge on here, all of the force on those charges will be the same no matter where it is on that field. Okay, so think about this. Think about what this is asking. It says if we place a 4 microcoulomb charge, so that's 4 times 10 to the negative 6, very good, is placed in a uniform field with a strength of 2 newtons per coulomb. So it's saying there are 2 newtons of force per every coulomb. All right, what is the force that it will experience? Well, think about it. We were saying the field strength is equal to the force over Q. Well, now we want to know what is the force. I'm sorry, this is an E, just so you can see that. This is the force. So how do we solve for that? Well, that's force equals the electrical field strength, which is what we've been given. Oh my goodness, I went backwards. The electrical field strength times Q. This is your field strength, and here is your charge. So if you rearrange, bang, you get your answer right there. And again, you're going to get 8 times 10 to the negative 6, but they have it as 8 microcoulombs, which is the same thing. If it said, hey, the field strength was 3, basically it's going to be 3 times the strength of the charge, okay? So there you go, pretty simple. All right, we're wrapping up here. So again, these are your important equations. That is for your definition of field strength. There's how you do your charge. And there's if we were to only have 1 point. Again, all of these can be sent off at right angles. They can be sent off at vector components, as I've talked about. All right, let's see if we can do this one. All right, calculate the electrical force that exists between an electron and a proton. All right, an electron and a proton. Now we're talking about electrical force. We're not talking about gravitational force. If we were talking about gravitation, we would use their mass. We're talking about electrical force, so we're talking about their charge. So we need to remember, what is the charge of an electron? Well, it was on a couple slides ago, but it's a negative 1.6 times 10 to the, who remembers? Anybody? Negative, don't say 6, that's micro. We're saying 1.6 times 10 to the negative 19th. Okay, guess what? A proton has the equal but opposite charge, so its Q is 1.6 times 10 to the negative 19th again. It's just not negative, right? Our radius is not going to be 2. Our radius is going to be 0.02. Okay, so we use the equation of F, electrical. We could write electrical instead of F of G. We could write F of E. F of E is equal to K. And who remembers what K is? Yep, K is 9 times 10 to the 9th. Good. Okay. Q1, which could be the electron, could be the proton. Q2 could be the electron or the proton, doesn't matter, just keep them equal but opposite, keep them separated, over R squared. Okay? So now you're going to plug and chug. You're going to throw this guy in for K right here. You're going to throw these guys in for your Qs. You're going to throw this guy in for your radius. Go ahead and do that real quick. Take a second, pause the video, come back, and we'll talk about the answer. All right, welcome back. If you did that, your F of E should equal 7.2. And it's okay. You could put negative. But it's really kind of like we're just looking for it. But you could put negative times 10 to the negative 6. Okay, that's newtons. All right, so there you go. All right, let me know if you got something different, but that's what I got. Again, two-dimensional, move at right angles. We can figure that all out. These are just like planets. They're just like balls being hit. It doesn't matter. We can figure out those angles as well. All right, last thing, and then we're done. So it says we have two 10 microcoulomb charges. Again, since it's micro, you might as well write 10 times 10 to the negative 6. You just might as well get it in your head that that's what's going to be. It's separated by 30 centimeters. As soon as I see that, I should be thinking that's 0.3 meters. What is the field strength between, what is the field strength between the charges 10 centimeters from A? So again, the whole distance here is 30, okay? But it just wants to know, what is it here? What is it right there, okay? Which is 10 centimeters or 0.1 meters, which means, again, this is 0.2 meters over here. We're looking for the field strength right there. So again, we got to find the field strength. We should be using our equation of F equals K, Q1, Q2 over R squared. If you do that, you got to pretend like this is a point. This is just a point charge sitting out here in the middle of nowhere. Okay, so if we figure from A, if we just look from planet A to that point right there, we do this. Here's our K. Here's our Q. Remember, the Q's are the same, but we're going to call this QA right here. All right, and there's our 10 centimeters or 0.1 meters squared. Okay, that's this part. That is literally just this part right here. Okay, we got to do the same thing though from this point charge over here. It's pretty similar, but it's a little different because of the radius. So again, here's our K. There's the answer to the first one up there. That's this first part. There's our K. Here, this is our QB. And the only reason this looks anywhere confusing is because they use the same number. If this was a 5, this would be 5 times 10 to the negative 6 down here. Notice the radius, our R, is 0.2 squared because we're 20 centimeters away from the middle. All right. And then we get this answer. And now the ultimate question is, you have a field strength here coming in, and you have a field strength here coming in. Are they going to add? Are we going to take these two numbers here? Are we going to add them or are we going to subtract them? The answer is you are going to subtract them. Why would I possibly subtract them? Why would I subtract these two numbers? And again, since they're both times 10 to the 6th, that's what they like to do. They go, well, you subtract them times 10 to the 6th, and you get this final answer down here. So why would I subtract them? Why would I not add them together? And it all goes back to the beginning. This is a positive 10 coulombs. This is a positive 10 microcoulombs. Since they're the same charges, they're going to repel. They are going to repel each other. So we're going to subtract it. If you were on a little spaceship in between these two imaginary, infinitely small little planets, you would say they're not coming in to crush me. I'm not going to feel a crushing force. They're actually going to be leaving me. They're going to repel. The force will be less. If one of these guys was negative, then these would have added together because they would have been attracted to each other. Okay? Again, I know these were a little longer than what we've been listening to normal, but that's okay. It happens sometimes. All right? We are not